Some of the most exciting developments in cutting-edge physics are taking place here in the UK. These include the world's most powerful lasers, particle accelerators, the development of renewable energy through fusion, new advances in plastic electronics, creating robots to investigate other planets, and exploring the universe using the latest technology in space science. Physics today provides us with a way of looking at the universe we live in. It covers everything from the nature of what we are made of to the size of the universe.
In this film, I'll be taking you on a journey to some of the most exciting cutting-edge physics in the UK and showing you some demos that will captivate the minds of students. By accelerating charged particles like protons and colliding them together, physicists can gain new insights into the origin of the universe. At CERN in Geneva, the hunt is currently on for the Higgs boson, a particle that physicists think is linked to the origin of all the mass in the universe. If we find the Higgs boson, we'll have the greatest insight ever into what the universe was like close to the Big Bang. But there's also a possibility that we won't find it, which in a way is more exciting because it means we'll have to go back to the drawing board and start again with completely new theories.
Particle accelerators are not only used for smashing atoms, they're also used for a whole range of applications, and they've thrown up some amazing discoveries. In South Oxfordshire, there's a particle accelerator known as the Diamond Light Source, which creates very intense beams of light that are being used in new and exciting ways. This includes studying the structure of matter at the level of molecules and atoms.
Diamond Light Source looks like a huge silver donut, and it is the size of about 5 football pitches. This facility was built in order to generate very intense beams of light. And by light, I mean anything from infrared or heat through to X-rays that might be used in medical imaging.
The Diamond Light Source, or synchrotron, is made up of 3 components: the linear accelerator, the booster, and the storage ring. Electrons start their journey in the linear accelerator. They are then transferred to the booster synchrotron, where they're accelerated to very high speeds in a vacuum similar to that in deep space. In the booster, they gain energy. When they're nearly at the speed of light, they're injected into the storage ring, over 0.5 kilometre in circumference. The electrons circulate and pass through specially designed magnets called insertion devices. As the charged particles travel around the accelerator, they produce very bright light, X-ray beams millions of times brighter than conventional sunlight and finer than a human hair. The X-rays pass through experimental stations where they are focused and filtered to generate detailed analysis of any solid, liquid or gas being studied.
Diamond is a great place to come to if you want to be a world-class physicist and apply your skills to as yet unknown problems. There is a large community looking at the structure of proteins and viruses. They wish to understand viruses, they wish to understand proteins in order to understand their function and, if possible, to find cures for particular diseases.
This picture here is a diffraction image. That happens when we put a crystal of a protein or a DNA or a macromolecule into a beam of monochromatic X-rays.
Essentially, this data here contains information about the whole of the structure of the object you're looking at.
That's true.
And then from that we can generate this picture here. Now tell me what I'm looking at here.
So what we're seeing in blue is a representative of the actual density of the electrons in a protein molecule. So into this chicken wire, if you like, we fit, this is a trace of the atoms within a protein.
Right.
So it gives us ability to develop new treatments for making sure the proteins stop working in your body, for example.
In other words, an antibiotic.
A novel antibiotic.
The particle accelerator at Diamond has produced some remarkable discoveries, and it's not just physics that will benefit from the electromagnetic rays that it produces.
We can demonstrate how a linear particle accelerator works using one of these. This is a Gauss gun, but instead of accelerating charged particles like protons, it's going to be used to accelerate these steel ball bearings. So there's a long track here, and I've got a very strong rare earth magnet wedged into the track here with 2 steel ball bearings on the other side. I'm going to put my safety glasses on just because the magnets can be a bit brittle. I don't want shards of it going into my eyes. And as I roll this ball bearing into the Gauss gun, the potential energy from the magnet will attract it, and that energy will be converted into kinetic energy, which will be transferred through all of these metal objects and should fire off this end ball bearing at an accelerated speed. So let's have a look. Now, of course, in a real particle accelerator, they wouldn't only use one magnet. There are a series of magnets within the accelerator. So I'm going to put another magnet in just here. We should be able to see that we get a greater acceleration. So let's have a look at that one. Okay, so we got a little bit faster there. Now, I've actually got 4 of these, so I'm going to put them all into the Gauss gun now, and we should be able to reach our maximum speed. And just for fun, I've got a few little skittles here, so let me line these up, and I'm going to see if I can knock these over. Right, let's see. So the magnets have accelerated our ball bearings here, just as they'd accelerate charged particles in a real particle accelerator. Lasers are one of the most important technologies to have developed over the last 50 years, and they feature across so many aspects of our lives. One exciting development is using lasers to produce affordable, sustainable energy, fusion energy, using the very same process that powers the sun.
The Central Laser Facility, part of the Rutherford Appleton Labs in Didcot, is home to the most powerful high-intensity focused laser in the world, the Vulcan laser. It creates fusion by heating matter to 100 million degrees Celsius. That's hotter than the surface of the sun.
The kind of way it works is you take a sphere of 2 isotopes of hydrogen, and we compress that with lasers, and we basically compress it to 1,000 times solid density. And what that does is move all the atoms much closer together. Then you need some kind of spark plug. So this is kind of like a nuclear petrol engine, right? So you do the compression, then you need to ignite the fuel. And so you take a really intense laser like the one we have here, a beam of something like 5 microns, which is a fraction of a human hair. So essentially what that's like is taking all the light that's falling from the sun on Earth and focusing it on the head of a pin and fire it in. And that produces hot particles, and those hot particles travel into the dense fuel and will raise it to the 100 million degrees centigrade. Now, obviously, we don't have all the sort of compression lasers or the general size of laser you need to get it to work. But what we can do in here is understand the spark plug physics. So what we do is we take our super intense laser, focus it onto pieces of material, and understand how those hot particles are generated and then how they deposit their energy.
The laser pulse concentrates approximately 10,000 times the power in the UK national grid onto a tiny spot. And in doing so, a very large amount of fusion energy will be triggered.
We are actually right now on the crux of demonstrating fusion by lasers in the laboratory. And once that very fact has happened, then hopefully we will hit the ground running. And for me, that's why it's so exciting. You know, it's a vindication of all the work we've been doing over the last 10, 20 years. So yeah, it's a good time right now.
It's hoped that in 30 years' time, the development of laser fusion will produce enough electricity to power most of our energy needs.
But that's not all. As well as using lasers, we can also release energy from fusion in a magnetically confined plasma. Plasma is the 4th state of matter. We're already familiar with the other 3, solids, liquids and gases. But if we take a gas and give it more energy, or heat it up, then the electrons that surround the nuclei of the atoms in the gas have enough energy to escape. So what we end up with inside our plasma are 2 species, a species of negatively charged electrons and a species of positively charged nuclei. And it's in this type of plasma that fusion can take place. We can have a look at some plasma inside this plasma tube. The first thing I need to do is remove some of the air that's inside here. Plasma has a lot of energy, so it takes up less space than a gas might. Rather than creating the plasma by heating it up, as we might see in a flame or something like that, we're actually going to create this plasma by passing a voltage across the tube. So as we turn it on, we should see the plasma appear. There it is. So could we turn the lights down, please? Now, when we have fusion going, we produce lots and lots of heat, and the plasma needs to be very hot to get that to happen. Obviously, there isn't any fusion going on right here, right now, but we need to keep the plasma away from the walls of the vessel that it's held in, and we do that using magnets. So if I bring my magnet up close to this plasma, you can see how it's possible to manipulate the plasma, move it around using this magnetic field, because the charged particles respond to the magnetic field. And when we talk about magnetically confined plasma, that's really all we mean, holding the plasma in place using a magnet. This technique of using magnetic fields to manipulate charged particles has been used to create the world's largest fusion experiment in the heart of the Oxfordshire countryside.
Scientists at JET, the Joint European Torus, are working together to develop an energy source that replicates the sun.
What we create here is essentially the hottest place in the universe. The plasma we see here is 150 million degrees, 10 times hotter than our sun, hotter than any star in the universe. And we're trying to create that to make electricity for the future, so it's an amazing place to be.
The machines used to do this are called tokamaks.
A tokamak is a device in which we want to make our own miniature sun, to replicate fusion here. In order to do that, we have to contain it in a vessel, and the vessel has to be a vacuum vessel, all the air pumped out for us to put our hydrogen in. And we then have to do what gravity does on the sun, which is hold the sun in one place and hold it all together. We have to do that with another method here, and we use very powerful magnetic fields. And we can see that very clearly here on this playback of a jet plasma, that the magnetic fields are pushing the plasma away from the walls, enabling us to heat it to these ridiculous temperatures.
And the tokamak is actually buried within the equipment, so there's a lot of diagnostics and electronics. This is one of the heating systems, so there's little tiny plasmas which are accelerated, neutralized, and then injected into the plasma to actually heat the plasma inside to 150 million degrees. So besides having the vacuum vessel in the middle, we need all of this equipment to run a fusion device. So yes, it becomes quite big.
One of the physics challenges we have with this plasma, as you can see here, is clearly wobbling here at the edges. It's quite similar to solar flares and sunspots and turbulence on the surface of the sun. Its activity we want to stabilise as much as possible, because the more stable our plasma is, the more easily and more routinely it will fuse and give us lots of energy out. So a lot of the physics has been in studying how we can stabilise and control the plasma to the best possible degree.
What you need to create fusion are two isotopes of hydrogen, deuterium and tritium. But JET only needs to take the amount of fuel equal in mass to a postage stamp. This is then heated to over 100 million degrees Celsius, and at these temperatures, the deuterium and tritium nuclei fuse, causing energy to be released.
This is really a place where physics is necessary and very important for us to succeed, and we have to understand and apply the physics that we have all learnt.
Fusion is an incredibly potent source of energy. Just a kilogram of fusion fuel can create more electricity than 10 million kilograms of fossil fuel. And unlike the fission process, which is another nuclear process, it doesn't create any long-lived radioactive waste. So it's clear that fusion, along with renewable energy sources, has a big role to play in securing our energy supply for the future. As well as replicating the fusion reactions that take place in the sun, physicists are working on new ways of harnessing the energy from sunlight. One of the hottest markets driving physics today is the application of plastic electronics to solar cell technology. The exciting thing is that we can take a plastic and change its properties, so that it can conduct electricity, act as a semiconductor, or emit light.
The Centre for Plastic Electronics at Imperial College here in the UK is one of the pioneering labs working in the area. The technology they're developing could trigger the next industrial revolution. Scientists at Imperial are turning plastic into electronic devices. A key thing here is to control the way in which the molecules assemble together. They're reorganised so that they emit more light and conduct electricity.
In my lab is really the focus on trying to arrange model structure in the sense of controlling how these polymers, these plastics arrange on the molecular level and see how they react then electronically, so that we really start to learn what is actually required, for instance, for high efficiency transistors or solar cells, and try to correlate them really onto the microscopic, actually even angstrom level. What is, I think, very exciting is in the case, for instance, of solar cells. There we really need large areas to be covered. So far we're really limited. I mean, the silicon solar cells, they're reasonably efficient at least. However, they're very rigid, so it really needs massive manpower to construct silicon-based solar cells. Versus with the plastic electronics, we hope really to be integrating the electronics into textiles or in architectural type of products, smart windows, house roofs. The future, well, my belief is really the solar cells, but also lighting system. The plastic electronic light emitting diodes, for instance, they are much more energy efficient, so you need much less power to warm them. And actually, contrary to a lot of lighting we have, they don't heat up. So therefore, actually, you don't lose a lot of the energy. So my belief it's in really in large area, flexible applications where plastic electronics will find their market.
Manipulating the way energy is transferred from one molecule to another in solar cells makes them better at converting light into electricity.
To illustrate this, we can use a demonstration of the fluorescence quenching of quinine, which is a molecule we find in tonic water. If I pour a little bit into my beaker. Tonic water fluoresces under ultraviolet light. So what that means is it takes the ultraviolet light that we can't see and re-emits it as blue light, which we can see. Now, if I take some salt and add it to the tonic water, the salt actually quenches the fluorescence, because as the energy is absorbed into the quinine and emitted as light, that's then absorbed by the salt molecules, which re-emit the energy as heat. So what we're doing essentially is changing the properties of this solution, of the liquid that we've got here, to manipulate and change the types of energy that come out. So with plastic electronics, obviously the process is a little bit more complicated, but we can manipulate it so that the energy that comes out is, rather than light or heat, is in the form of electrical energy. Today's solar cells are pretty rigid and bulky, but in the future with plastic electronics, solar cell technology could be incorporated into many of the objects that we use every day. So solar cells could be woven into our backpacks so that when we carry around our laptops we're charging up the batteries, or they could be used to make television screens that can bend into view. Or how about an electronic newspaper that's paper thin but can be uploaded daily with your news so you can read it electronically. All of the physics topics we've covered so far have addressed some of the major challenges facing society. But there's one big question that all scientists want to know the answer to. Where does life come from? To try and answer this question, UK researchers are sending robots equipped with the latest high-tech physics instruments to explore other planets.
A robotic rover is being developed by Astrium in Stevenage for a planned mission to Mars in 2018. Named Bruno, the robotic rover is about the size of a small golf buggy, and its mission is to examine Mars's geology and search for signs of past life.
The really unique feature of the ExoMars rover will be the fact it's capable of making its own decisions about where it can and can't go, and therefore generate its own path. This has never been done before. Each wheel has 3 separate motors it can use. We can do what's called an Ackermann turn. That's what cars do when they sort of follow a curve. We can spin on the spot, which is particularly useful if we're surrounded by rocks, or we can move sideways like a crab.
Bruno will have a drill for extracting rock samples from up to 2 metres beneath the surface, and a mini lab will analyse what's been brought up.
The physics that we have on Earth are equally applicable on Mars. Gravity is present in both. Here, the acceleration of gravity is 9.81 metres per second squared. On Mars, it's 38% of that. So what we have to do is here try to replicate the weight of the rover on Mars when we're testing on Earth. The other aspect is thermal control. Mars has an atmosphere, so you have to control the temperature. So we actually have devices on board called loop heat pipes, which are actually very similar to what you have on your fridge in your kitchen. You get sand dunes on Mars. You know, we have sand, and sometimes it's cohesive, it sticks together. Sometimes it can be very loose and you just sink into it. And friction is part of that phenomena as well. So friction and stability is quite a challenge. The target for operation on Mars is nominally travel 70 metres in a Martian day. A Martian day is about 36 minutes longer than an Earth day. But Mars is cold, so it's been that at night time the environmental temperature has been down at minus 130 centigrade. So we have to thermally condition the motors, the lubrication system, the battery needs to be up to temperature. So we have to bring everything up to temperature before we can start moving.
One of the cutting-edge instruments that will help the rover in its search for evidence of life is called the Life Marker chip. That will test soil samples drilled from beneath the Martian surface.
The Life Marker chip is an instrument which will use solvents to extract organics from the Martian soil, or regolith as scientists call it. Take those organics, concentrate them using evaporation, so physics comes in there, and then pass them into essentially an assay chamber where you have molecules which will bind on to those organics. Potentially we're at the stage where in 10 to 20 years we might know whether there's life on the surface of Mars or even potentially life around planets and other solar systems, because astronomy techniques are coming on. We're beginning to find planets around other stars, and in 10 to 20 years time we should have the technology to be able to actually look at the atmospheres of those planets and see whether there's things like oxygen.
It would be the greatest discovery in human history to find life outside the Earth. Space is a very unforgiving environment, and if you get it wrong, it will damage and potentially end your mission.
The UK could soon become a world leader in professional service robots. These robots could do anything from moving people and baggage around airports to assisting surgical teams. More than ever, physics in the 21st century is an example of international collaboration, especially in the areas of astronomy and cosmology.
The Space Science and Technology Department in Oxfordshire is a pioneer in space research. They're using physics to test whether the instruments we're sending into space can withstand the forces they'll be subjected to during takeoff. A testing facility simulates the vibrations of loads launched into space. Scientists in the department have designed a classroom activity to simulate the launch of rockets. It uses models on a vibrating table attached to an oscilloscope that measures the G-force.
We gave each team of students a design challenge to build a device that would hold an egg on a simulated launch. We used spaghetti and marshmallow. So a lot of them came up with various ideas on how they'd hold an egg. And then what we'd do with the equipment is load in an egg, and then one at a time we'd run them up and put them against each other. But the point was, the fun bit of it was we could test to destruction, which is something obviously we can't afford to do on the real stuff. But what we try and do is try and make them realise that what they're doing for fun, this is what we actually do in real life.
The department is also doing pioneering research in the area of solar physics.
One of the big questions that we are trying to answer in the whole of physics is, how does the sun affect the Earth? We can do this in a number of ways. We can take in situ measurements of particles coming from the sun towards the Earth. We can take radar measurements of the effects of solar activity at the Earth. There are a number of different satellite missions that are in use at the moment, and they are in different places in the solar system to look at the sun and to study the sun.
Physicists are working on the design and build of many of the world's major telescopes on Earth and in orbit.
We're at a very exciting time at the moment. There are going to be new spacecraft missions coming up in the not too distant future. There will be large telescopes being built on the ground in the not too distant future. So we should be able to get a better understanding of the laws of physics and how they connect to each other.
Physics is fundamental to the basis of nearly all the sciences. Physics describes how matter interacts, it looks at the forces associated with them, and that leads on to how chemistry works and ultimately how biology works.
Space science has the ability to inspire the next generation of scientists who can help us answer some of those big questions. Today's physicists are at the forefront of scientific research, but there's no doubt that over the next 50 years, the contribution of physics to science, engineering and technology will be even more exciting.